Hi folks, thanks for coming out. My name is Mauve, my pronouns are they, it, and today I'm going to be talking about peer-to-peer databases and how you can build them on top of IPLD Prolly Trees. Now, before we get into peer-to-peer databases, let's talk about how regular databases work and how they can serve data so fast. At the core, most database engines consist of a query layer that sits on top of collections of data and indexes over that data, which speed up searches. So let's talk about the indexing bit. What does it mean to search through data without an index? To start, if you want to search for data related to a given query, you'd need to search through all of your data in order to know if you satisfied that query. What's more, if you want to perform a sort on your data at the same time, you'll need to do that in tandem with filtering and buffer the order of the results, either to disk or in memory as you go. This is fine for small data sets if your CPU and disk are fast enough, but as your data grows, so would the latencies for searches. Database indexes are separate collections that sit alongside your main data, but instead of having the full data that's sorted by VID, it's just one or two properties that are sorted by value. What's convenient is that you can have all the data sorted ahead of time and can quickly seek to what you need and skip anything you don't when you perform a query. This is also very useful for streaming results in. Instead of waiting for a full query to finish, you can start processing data as your application gets it and as soon as it's available. So databases typically use B+ trees for storing indexes. You can think of them as key value stores where the keys are bytes and are sorted from lowest to highest. B+ trees also have the property of being efficient for seeking into a sorted list and to then sequentially read ranges of key value pairs from that. Here's a rough picture of what the structure of a B tree looks like. Data is stored and stored sequentially in leaf nodes, and there's intermediate nodes that are created that point to the leaf nodes along with the starting key within that leaf. You can then replace individual leaves or intermediate nodes up until the root without needing to update the rest of the tree. You can also quickly search through the tree to find the leaf node that contains the start of whatever range you're seeking. The way it works is you start at the root, you find the closest leaf to the key you're searching for, then you traverse down and repeat until you reach an actual leaf, and from there you can start doing a sequential read and follow the pointers to the next leaf with the rest of the range you're seeking. So one of the downsides of B trees is that the order that you insert or delete keys can change the shape of the leaf nodes and how everything links together. For example, if you insert into a tree that had a key deleted before, or if you insert in a key that got deleted after, you can have different boundaries between leaf nodes. This makes them less suitable for distributed systems where peers are authoring and replicating changes in different orders. An alternative is to make use of another data structure, Prolly trees. They're like B+ trees in that you have ordered key value pairs within leaves stitched by intermediate nodes. However, instead of using pointers in memory and chunking keys as they're written, each leaf and each intermediate node is content addressed, in this case using IPLD. As well, when keys are being inserted into the structure, boundaries between leaf nodes are calculated based on the content address of keys rather than on insertion order. This means that regardless of the order that keys are inserted, each peer would come to the exact same structure for their tree at the byte level. Here's what it looks like at the schema level. The root of a Prolly tree has information about how the tree was chunked so that that tree can be easily updated or merged with other trees without having to hard code those chunking settings for the entire application. Each tree node then has a list of keys and a list of values that go with those keys. It also has an isLeaf boolean that lets the application know whether this is a leaf node, which contains actual values, or if the values are links to further tree nodes. So here's a gist of how you construct a Prolly tree, or how you can go about updating a portion of it. What's useful is that it's a bottom-up approach, and you can build the tree as you ingest data. So first you start by beginning to add keys to a leaf node. So as you're doing this, you're going to be checking for chunk boundaries for each key value pair. And once you've discovered a boundary, you create a parent node if one doesn't exist, and a sibling node. You add all remaining keys to the sibling, and you add the current node and the sibling node to the parent. Then you repeat this process for the sibling, and after you've processed all the keys, you go to the parent nodes and process them, and then keep going up until you have a new root node for all of your data. So with this, you'll have a balanced tree where you'll have chunk indexes where you expect them, chunk boundaries where you expect them, and you'll have sequential keys to read in your application. So the boundaries between leaves can be calculated based on a chunking threshold. This is an integer that's used to determine the probability that a new chunk should be started. You take the hash of the given key value pair, and if it's less than the threshold, then you know you need to put all subsequent keys into a new chunk. This is reminiscent of the hash cache algorithm used in things like Bitcoin. The lower your threshold value is, the less likely a boundary will occur, and the larger your tree nodes will get. So from here, you can start worrying about the details of trees and focus more on the key space. Here's an example of how you can segregate the key space for a collection of posts. You can have a top-level prefix for everything related to posts. Then you can have a longer prefix for all the individual documents in your database that are posts. And finally, you can have separate prefixes for each index over those posts. With this, you can do sequential reads on documents and different indexes and avoid overlap between different collections within a single dataset. For example, here's what an index with a few posts could look like. We take the created at and tags property out of each post, and we make a new index key which points to the post's ID. Notice how everything is sorted by the timestamp. So you can seek to a start time and filter out irrelevant tags without fetching the full post. In this example, we have 3 posts, but what if you have 1,000,000 and only want the most recent 50? Well, you can seek to, today, get the first 50 posts that match your query and ignore the rest of the DAG entirely, skipping all of that extra loading. That's because with Prolly trees, the network is your database. As you query the key space, you'll be loading parts of the DAG using either block exchange or graph sync or whatever other replication protocol you want. And instead of replicating everything and then making it usable, you can start loading data and just the data that needs to be on the page now. You can also load more data in the background to speed up subsequent searches and to be available while offline. When merging datasets, you can skip any equivalent branches and stitch in new branches without having to fully traverse the values. Combined, this lets application authors focus more on their data and making efficient queries, not worry as much about initial load times. There's some trade-offs to consider. However, if you choose to have larger chunks on average, you'll end up having them updated more often as keys are added and changed. At the same time, if you have smaller chunks, your tree will be deeper and you'll potentially need to do more round trips to load it. On the indexing side, the more indexes you have, the more duplicate data you have. But these indexes are important for making your queries efficient. Sometimes it could be the difference between scanning across all your data and having poor UX while you wait for that to happen, or having a bunch of duplicate data and using up extra storage on your device. Generally speaking, you'd be making indexes for data locally if it's not on the network, so it's usually worth it. Lastly, the question of how to merge data from multiple sources is nuanced, and there's a lot of ways to do that depends on your application. You might be using CRDTs, you might have a last right win strategy, you might have some other thing I'm not going to bring up now. And even though we have these useful structures for indexing, there's still a lot to be done at the application layer to make these databases useful. So hopefully that's given you some more insight into how this stuff works, and maybe it sparks some ideas on how you can build your own databases too. If you're interested, we've got a spec for how this can be implemented using IPLD, and we've got a matrix channel where we've been chatting about peer-to-peer databases in general. So come check out our source and join us in building efficient and usable peer-to-peer apps. Thank you so much.